Hello, in this video we will be talking about Bernoulli's principle formula. The Bernoulli's equation formula is a relation between pressure, kinetic energy and gravitational potential energy of a fluid in a container. The formula for Bernoulli's principle is given as follows. P plus half rho v square plus rho gh equal constant, where P is the pressure exerted by the fluid, V is the velocity of the fluid, rho is the density of the same fluid, and h is the height of the container. Bernoulli's principle is a key concept in fluid dynamics that relates pressure, speed, and height. Bernoulli's principle states that an increase in the speed of a fluid occurs simultaneously with a decrease in static pressure, or the fluid's potential energy. After studying this formula, we can conclude that when the area where the fluid is passing decreases, the velocity automatically increases to conserve the flow rate. Consequently, the pressure decreases. And more details will be seen and acknowledged during the upcoming experiment.
In this experiment, we will study fluid dynamics using a plastic bottle full of water. Before we begin, get a water bottle and cut 3 holes of the same size but different heights. Then fill the bottle while covering the holes to avoid any spillage. Bernoulli's principle states that the flow velocity of water out of each hole should be determined only by the distance of each hole below water level. Start uncovering the holes one by one to observe the different results. As we can see, the lower the hole is, the farthest the water will travel, which verifies Bernoulli's principle.
For our second experiment, we are going to implement Bernoulli's principle in a different way compared to the previous experiment. In the previous experiment, we saw how water plays a role in the application of the principle. As for this one, we're going to see the effect of air. For this experiment, we need just a hairdryer and a ball. What we're going to do is turn on the hairdryer by placing it vertically as so, and we are going to place the ball right above the hairdryer so that it is in the airflow. We are going to observe for how the ball moves in the flow of air, and then see what happens when we tilt the hairdryer left and right. Lastly, we will provide an analysis for why the ball moved the way it did using Bernoulli's principle. As we can see, the ball stays in the airflow, whether the hairdryer was left straight upwards or tilted. The ball slows down the air as it exerts a downward force as the air strikes it, while the air applies an upward force on the ball that makes it move up. This keeps the ball in place.
Now we're gonna give you a little representation of what happened in the experiment. Here's our hairdryer, here's the airflow, and the ball being struck by the air. By Bernoulli's principle, with the air moving rapidly, it creates a low pressure zone. This brings about the question of why didn't the ball fall off to either side? As we noticed, the ball was wiggling around above the hairdryer like it was about to fall off. So we can observe that the ball does move to one side of the airflow, and then there would be more air passing by its side, creating the low pressure zone right here. And on the free end we have normal pressure, or relatively higher pressure. This pressure difference pushes the ball back into the airstream, not allowing it to fall off. This could happen on either side, whether on this side or this side. With the side that is free would be normal pressure, and air passing through would create a low pressure zone, with the pressure difference pushing the ball left and right. And when we tilt the hairdryer, this is what we would notice. Hairdryer being tilted and air going also at the angle that it's being tilted, and the ball consistently stays on one side. The air passing from the other side creates the low pressure zone again, and on the free side there is normal pressure. So again, this pressure difference is what keeps the ball in the stream of air.
One thing to observe during the experiment is that we were cautious about the angle to which we tilted the hairdryer. This is because if we over tilted it, gravity would be significant enough to pull on the ball and just throwing it completely out of the airstream, making it fall off from the hairdryer and the flow of the air. So as Eliyo stated at the beginning of this video presentation, the main principle that we are applying in our experiments is Bernoulli's principle, and his equation is P plus rho v squared over 2 plus rho gh equals to constant. However, to be able to use this equation in our experiments, there are some restrictive assumptions that had to be made, including the flow must be steady, incompressible, and frictionless, the flow must be along a single streamline, and there must be no shaft work or heat transfer between two different points that we may be analyzing. For our experiments to work and give us the results that we were looking for, we are sure that we have followed these assumptions in order to be able to apply Bernoulli's principle in our experiments.
In conclusion, the investigation into Bernoulli's principle has provided valuable insights into the fundamental principles governing fluid dynamics and their applications in various fields. Through theoretical analysis, experimental demonstrations, and real-world applications, it is evident that Bernoulli's principle plays a crucial role in understanding the behavior of fluids in motion. The principle states that within a steady flow of an ideal fluid, an increase in the fluid's velocity occurs simultaneously with a decrease in pressure. This relationship between velocity and pressure has wide-ranging implications, from explaining the lift generated by aircraft wings to the operation of venturimeters and other fluid flow devices.